So welcome back, gang. Today we're going to pick up where we left off last time. We're going to talk about some more applications of the derivative. Other news, your tests have all been graded, right? The scores are all in. It took me until I think for your group, I don't remember if your tests were graded before our last meeting or not. I'm doing way too much grading, but definitely everything is in. So yeah, we're going to move on from there. Let's get to it. I also owe William an apology. He was trying to get a hold of me all weekend, and I was pretty hard to reach. I know we
yeah. By the way, about that, you said you were going to be free on 3 p.m. on Saturday. What happened?
Yeah, I'm not sure. So I was looking on my phone, waiting for your email to come through, saying like yes or with another time, and I never showed up. And then when I looked here on Sunday on my computer, I did see your email, and it had come in like right after I sent it. So I don't know, my phone wasn't refreshing email or something like that. I had issues with my T-Mobile service over the weekend, but I'm really not sure. So I definitely owe you an apology. Had I checked my email on my computer instead of my phone, I would have seen it. So I am sorry about that. That should not have happened the way it did.
No, you're good. You're good. Just to confirm, though, just like very quick thing. Things that go over. Relative and absolute extrema, points of inflection, concavity, and the mean value theorem.
Yeah, those are the big points. And if you're able to come by this afternoon, right, we can talk a little bit in office hours.
I will be able to do that for 15 minutes because I have class from 1 to 1:45 for English, but it's from 12:30 to 1:45. But
1:45. All right, yeah, if you can slide through for the last few minutes of that, we can hang out and talk a little bit. And then if you can send me the materials that you're planning to present with, we can talk about the format. You're going to use PowerPoint, you're going to do a live lecture. Try to get some of those things sorted out and let me review the materials either tonight or tomorrow morning, and then I can get back to you with any changes I recommend.
All right.
Alrighty, so yeah, definitely sorry about that. Let's get into today. So this is MAC2311, sections OH1, which is Calc 1 honors. And today is the 11th of October, 2021. And Yiping, I spoke a little bit with Brett. I understand that you were able to talk with him, but that he wasn't really willing to help you too much with the statistical analyses. That's a bit disappointing, but also understanding because he's a busy man and that would be quite a lot of work. So my understanding is that he pointed you to some people at the Learning Commons who might be able to help. If they are helpful, that's wonderful. It's possible that the questions you're asking are a little bit over their head. If that turns out to be the case, let me know and I can help you hunt some people down who know statistics better than me and maybe have the free time to help a little bit more with the details there. But today, we're going to talk about linear approximation. And we're going to talk a tiny bit about differentials. I really hate the way your book covers differentials. It's a sloppy and lazy thing that they do where they abuse a lot of notation and lots of shaky equal signs. And I like to minimize that as much as possible. So we're going to be thinking of this from the linear approximation standpoint, but I'll also introduce the notation for differentials. And we'll come back and talk more about differentials later when we get into section 5.5, which is a fair ways down the road. So the bulk of today is all about linear approximation. And the big idea is that, how do we want to say this? Some functions are hard to evaluate at certain inputs. For example, the sine of 1 radian or the square root of 4.3 or I don't know, what are other good examples of functions that are hard to evaluate? How about the inverse cosine of 1.5, right? These are all tough numbers to come up with. we know they exist, right? 1 is definitely a number that's in the domain of sine. Sine's domain is all real numbers. Oh, inverse cosine of 1.5 does not exist. Sorry, let me back that up. How about the inverse cosine of 0.9? But yeah, these are things that are a little tough to come up with, right? Or the square root of 4.3, I'm not too sure what that is. I know it's a little bigger than 2. The cosine of 0.9, I don't really have a clue. It's some angle such that the cosine of that angle is 0.9. So some functions are tricky to evaluate at certain inputs. So instead of plugging into those functions, we can plug into a tangent line at a point of tangency that is both nearby and easy to evaluate. So instead we find, I kind of gave it away, we find a simple related function which we trust will give a good approximation and plug into that. And the related simpler function, as I said, is going to be a tangent line. That's the idea. The simpler function, I'll just say it. This will be a tangent line. And kind of the meta idea, or the big idea, is that the best linear function to approximate any function f of x, any differentiable function f of x near x equals a is the tangent line to f of x at x equals a. And I'll say one more thing kind of in this high level way of thinking about it before we get in. In slightly more advanced, no, the sine of 1 is not 0. The inverse sine of 1 is pi over 2, but the sine of 1 is not a nice number. Over here. It's weird, right? 0.84, blah, 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 blah. If we're looking on the graph y equals sine x, the point 1 comma sine of 1 is right here. So I'd be looking for this y value, right? And that y value is a weird y value. I'm not aware of any nice way to write the sine of 1 besides the sine of 1. What's the same? In a certain kind, so there's many different flavors of like grown-up or advanced calculus. One of them is real analysis. Another one is complex analysis. Another one that's especially useful if you're into physics is differential geometry. Differential geometry is the mathematics that goes on underneath general relativity. When people talk about space-time being this curved four-dimensional thing, they're doing differential geometry. The study of manifolds is differential geometry. It's the study of smooth surfaces. From the perspective of differential geometry, the derivative is the unique linear function that best approximates f near a given point. So the derivative of some many-dimensional function at a point is the unique linear function, it's usually written as a matrix, unique linear function that best approximates that many-dimensional function near that point. So this idea that the best linear function to approximate f near x equals a is the tangent line is kind of you can define the derivative this way. You can use this sentence as a definition of the derivative. You just replace the words tangent line by the line with this slope. And then you say that slope is the derivative. Okay. I'm going to draw for you a picture. I don't know if I had to label it as picture. We know it's a picture, but here's the picture. Here's my x-axis, and I have some curve here. So the function I'm graphing is f of x. This is the graph y equals f of x. I'm going to tag this x value right here as just x. And what I want is the y value of this point. That would be f of that particular x. So I want the value, thinking here of x is a fixed constant. I want the value of f of x, but it's hard to find. Maybe it's like the sine of 1 or the square root of 4.3. Hard to compute. So what I do instead is I come to some nearby point A, maybe A is over here, and I construct the tangent line to F at this point. So here's my tangent line. I'm going to do my best to draw it in a reasonable way. And I'm going to call that tangent line by a name. I'm going to call it L of x, right? It's a linear function, hence L. And I'm thinking of it as a function, right? So you like solve the tangent line for y. The crucial observation is that this y value is very close to the y value I want. Right? That's the big idea. So instead of finding the black y value directly by plugging into my function, I construct this blue function, which is the tangent line, and I plug into that instead. And the way we would say this is, so if x is close to a, then the output from the function f, which is f of x, will be very close to the output from the function L. Okay, so if I want the y value of this black point, which is tough to find, like the sine of 1 or the square root of 4.3, I can come over here to some nearby point A, where I know the output for that function, like the square root of 4, I know that, the square root of 4 is 2. I can come over here to some nearby point where I know the output, construct the tangent line, and then plug into the tangent line instead. Because the tangent line does that thing where it just kisses the graph, it is actually the best linear function for approximating the original. In other words, there is no line that goes through this point that would get you closer to this point than the orange here. That's the big idea. This is what we mean by linear approximation. The black function is not a linear function. And it's possible that it's quite hard to get the function values out. The blue function is a linear function. And it's very easy to plug into linear functions. You never need to do any complicated operations, right? You never take a sine of anything or take a square root of anything or do any shit like that when you're plugging into a linear function. You just multiply by a number and add some number, right? And that's it, that's done. Let me show you in Desmos a specific example. Let's come back to the sine of 1 really quick. You don't have to write anything down for what I'm about to do. Once you have what's on your what's here in your notes, you're good. I just want you to think along with me for the next part. All right, I want the sine of 1.
We can't see your screen.
No? Okay, this is weird. Sometimes it does that. Turn off share screen. Here you go. Better?
Yeah.
Okay, wonderful. What nearby point here could I try? Well, I could try like, where's pi over 3? The sine of pi over 3 is 3 over 2, right? So look here, really close. Let me color code things the way they were before. So I want the y value of the black point. Let's make the sine curve black. And I'm going to use my nearby nice point as this blue point. I want to know what is the sine of 1. That's the y value of this black point. And in service to that, I can construct the tangent line. I'll call this f of x as y minus f prime of pi over 3. Oh, sorry, y minus 3 over 2 equals f prime of pi over 3 times x minus pi over 3. We'll make this blue. The blue line is the tangent line at the blue point. Instead of calling this y, I can call this L of x and then add this over. Plus. All right, you see it's the same tangent line. I've just solved it for y. And now I could ask, what is L of 1? And you see how good this does? 0.842, 0.841. If you zoom way in here, I can look at the point 1 comma L of 1. Way in here. Here's the ultra zoomed in version. I got to come out a little bit so you can see the tangent point. So over here, this is a comma f of a. That's my point of tangency. I'm after this black y value, which is hard to compute, but I can find the blue y value very easily. So I'll show you exactly how to do this, but this is what's going on. In order to approximate the black y value, I construct the blue function, which is just a tangent line, and then you plug into that instead. And you'll see plugging into that blue function is easy. And as long as you stay close to this point of tangency, the blue line will stay very close to the black curve. So if I wanted to approximate any of these y values, all of which are hard to do, except for this exact one, if I wanted to approximate any of the y values on the black curve, I could plug into the blue function instead. Plugging into the black is hard because you have to take the sine of something. Plugging into the blue is not hard. All of these are constants. The only place you have to actually plug something in is right here. So let me show you how to do it. The first example I'll use will be simpler. Well, no, wait, let's go ahead and do that one. Let's go ahead and do that one. Okay, so we're going to the term for that blue function is called the linearization of f of x equals sine x at x equals pi over 3. I'm choosing pi over 3 because I know pi over 3 is close to 1. So remember, the idea here is that I want the x value of my point of tangency to be quite close to the x value where I'm plugging in. The x value that I'm trying to plug in is 1. The closest number to 1 that I know the sign of is pi over 3. Pi is like 3.14159. So when you divide that by 3, you get something very close to 1. The linearization is that function L of x, which is the tangent line. Which is the tangent line solved for y. And I'll give you a formula for L of x, but really the way to think of it is the tangent line solved for y. It's just easier than memorizing a new formula. So what we're going to do is we're going to find the tangent line to f of x equals sine x at x equals pi over 3. Then we're going to solve that for y. That will be my linearization. Then we're going to plug 1 into that. So first we got to find this tangent line. This is a problem we could have put on the first exam for sure. We know we need a point and a slope. So the point here, when x is equal to pi over 3, f of pi over 3 is the sine of pi over 3. What's the sine of pi over 3?
1/2 or square root of 3 over 2.
The other one, yeah, root 3 over 2. So my point is, point of tangency will be pi over 3 comma root 3 over 2. For the slope, I know I need f primed of pi over 3. So I compute f primed of x, which is the derivative of sine, is cosine. So my slope is f primed of pi over 3, which is the cosine of pi over 3. And this one is 1/2. Right, cos pi over 3 is positive 1/2. Therefore, the tangent line I'm looking for is y minus root 3 over 2 equals 1/2 times x minus pi over 3. And we can solve this for y. That would be, and if we want to put all the pieces, I'll distribute and put everything together. So this is 1/2 x minus pi over 6, and then plus the square root of 3 over 2. I don't feel especially compelled to combine these two things together, although you could. Maybe, nah, let's not do it. Okay, so this is my L of x. This is the linearization. Think about what the word linearization might mean. Linear obviously means linear. This ization part of the word, if I'm going to describe this, when you talk about normalizing something, you're making it normal. When you talk about, what other words can I use here? Can't think of other good examples here, but like it means to make linear, right? So the linearization is our best effort at making the function linear. So L of x here would be 1/2 x minus pi over 6 plus the square root of 3 over 2. Now, we just plug x equals 1 into L of x. So I know that the sine of 1 should be really close to L of 1, right? Because the tangent line stays close to the function. Oh, sounds like my internet might have just dropped. Yeah, it's been doing that. Am I still on the hotspot? Can you guys hear me?
We can hear you.
Oh, good. Okay. Yeah, internet here has been going in and out. I had to switch to my hotspot. I think we're probably still on the hotspot, so we should probably be good. Since the tangent line stays close to the curve, we know that the sine of 1 should be very close to L of 1 because L of x is the tangent line. And then L of x itself is exactly what you get when you plug 1 into this, which is 1/2 times 1 minus pi over 6 plus the square root of 3 over 2. So that's just 1/2 minus pi over 6 plus root 3 over 2. Now, is this a decimal? No, but that's okay. I know what each of these things are. This is actually really close to the sine of 1. And that's what we're looking for. So if I asked you, give me a good approximation for the sine of 1, if you said 1/2 minus pi over 6 plus root 3 over 2, I would be like, awesome, correct. Now, is this nicer than the sine of 1? That's kind of a matter of opinion. It depends on how comfy you are with each of these things. But I would say yes. I would say yes, because technically to compute the sine of 1 requires an infinite process. The only other way to compute that number is through something called a power series. And power series are beautiful and in some ways elegant, but in other ways very unpleasant objects that you'll work with a lot in Calc 2. So the sine function, besides having the geometric definition, if you need it for computation purposes, is usually defined as a series, which obviously is not pleasant. It contains infinitely many terms, whereas this just has 3. So yeah, this number, whatever it is, very, very close to the sine of 1. All right. Questions on the procedure or the notation? So again, we were looking for the y value of this black point. Instead, we found the y value of this blue point. And because the blue is a tangent line to the black, we know that the y value on the blue is close to the y value on the black. And this is exactly what we got. Another fun example here I'd like to use is computing the square root of 2. And this one I think you may like more because the numbers are nicer. This is usually what I use as a first example. I'll do this with a non-honors class. So we're going to approximate the square root of 2 by using the linearization of, well, what function would make sense? What function gives the square root of 2 as an output? What's the most natural choice?
Cotangent? No, sorry.
Maybe we could use some trig stuff if we got very clever, but even simpler, much, no trig here.
Pythagorean?
Well, we're looking for a function like f of x equals some function. What sort of function spits out root 2? Don't overthink this, I promise you, very simple. It's a non-honors question. Yeah, the square root of x. It came in chat, Talia got it. So the square root of x is definitely going to spit out root 2 when you plug in x equals 2. Now, the other thing we need is a nearby input whose square root is nice, right? Like I used pi over 3 as my point of tangency for approximating the sine of 1 because I know the sine of pi over 3. I could use the base point of 1. 1 is somewhat close to 2. Are there any perfect square numbers that we can think of that are closer to 2?
4?
4 is a little further from 2 than 1 is. So yeah, 4 would work. But I think I would get a better approximation using 1 than using 4. I can get sneaky on this. See, I'm not thinking of an integer, but 9/4. 9 is a perfect square, 4 is a perfect square. That ratio I could easily plug in here and tell you what the answer is, right? F of 9/4 is 3/2. So if I use 9/4, that is much closer to 2 than either 1 or 4. So this coming up with this is somewhat the clever part here. You have to choose the function you're going to use, and you also have to choose the nearby point. In practice, the problems I'll be giving you guys, at least the simpler ones, this will be given to you. The problem would be stated exactly like this. But out there in the real world, if you as engineers, physicists, chemists, whatever, want to do this stuff, you need to come up with your function and your nearby point on your own. 9/4 is a good choice because I know what f of 9/4 is. It's easy to plug that in here. I get 3/2. And also 9/4 is really close to 2. 2 is 8/4. So this is pretty good. But again, normally this would be given to you. So what you're responsible for is what follows, the purple. Again, we need to find the tangent line. To f of x at x equals 9/4. And to that end, I need a point and a slope. The point of tangency here, I know that f of 9/4 is the square root of 9/4, which is the square root of 9 over the square root of 4. Remember, while square roots don't play nice with addition or subtraction, they do play nice with multiplication and division. The square root of 9 is 3, the square root of 4 is 2. So my point is 9/4, 3/2. 3/2. And I can show you in Desmos that that is indeed a point on the graph. Whoa, 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 whoa. All right, there we go. And 9/4, 3/2. Zoom out. So here's the square root function. That was the function that we were drawing in black before. And here's my point of tangency, the point we're putting in blue before. The point that I'm after the y value of this black point here. And the way I'm going to get it is by constructing the tangent line at the blue point and then finding the y value on that tangent line. So I'll add the things to the picture here as we come up with them here. Before we can write down the tangent line, we need the slope. That means I need the derivative, which is d dx of the square root of x, which we calculate using the power rule. That's d dx of x to the 1/2. So this is 1/2 x to the -1/2 which is 1 over 2 times the square root of x. Now that's the derivative. My slope is going to come from plugging a number in. M tan, the slope of my tangent line, is f primed of 9/4, f primed of the x value at the point. And there is some algebra to do here. This is 1 over 2 times the square root of 9/4. We've seen that the square root of 9/4 is 3/2. So this is 1 over 2 times 3/2.
1 over
Yeah.
3.
Yeah, and then downstairs the 2's cancel, so this is 1/3. All right, hence my tangent line is y minus 3/2 equals 1/3 times x minus 9/4. And we're going to solve this for y. I'll go ahead and do this. I'll write it like this first. 1/3 x minus 9/4 plus 3/2. That would be L of x. And we can clean it up, right? So 1/3 x. 1/3 times 9 over 4 is minus 3 over 4. And then we have to add to that 3 over 2. So that's 1/3 x. 3 over 2 is the same as 6 over 4. 6 over 4 minus 3 over 4 is 3 over 4, right? I said that right, yeah. Multiply by 2 over 2, you get 6 over 4. 6 over 4 minus 3 over 4 is 3 over 4, yeah, positive 3 over 4. So that's L of x. Let me go ahead and slide that into my picture now. There it is. All right, so here we are. I've got my point of tangency where I constructed the tangent line. I'm after the y value of this nearby black point. And in order to get that, I will look at the blue function there. And what is L of 2? So I can see from the picture that the y value here is close to the y value here. In fact, it's very close. And we can get a really nice expression for it. So therefore, the square root of 2, which is exactly equal to f of 2, should be very close to L of 2. And L of 2 is exactly equal to 1/3 times 2 plus 3/4, which is 2/3 plus 3/4. And if we want that as a single fraction, the denominator would be 12. This would be 8/12. Plus this would be 9/12. And 8 plus 9 is 17. So the square root of 2 is very, very close to 17 over 12. Now, is the square root of 2 equal to 17 over 12? No. Right here at this step, we have an approximation. The difference is exactly the difference in the height between these points. But if you zoom out to the sort of scale that we're normally thinking on, which is like this, I can barely even tell the difference. They are so close. How off are we? Well, as a decimal, the square root of 2 is 1.4142, blah, 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 blah. It's irrational. As a decimal, 17 over 12 is 1.4167. So we're off only in the third decimal place. This is a very good approximation. All right, what is the difference? 0.002. 0.002453. So this is very accurate. The error is about 0.002. Which is great news, right? I mean, this is wonderful. Most people know the square root of 2 is close to 1.4. That's good enough for them. Here, we know that the square root of 2 is like 1.41, which is good. Even better, we have a rational approximation. This is nice, right? Rational numbers are so much easier to work with than irrational numbers. So if I needed to do some computation with the square root of 2 somewhere, instead of having to leave it like that and just stomach it, I could say, it's really close to 17 over 12 and work with this instead. Okay.
I have a question. In the exams, the equation, do we need to set up the equation by ourselves?
It's a good question. Good question. Yes. So on an exam, I would give you a problem stated pretty much just like this. So I'd tell you what we're approximating, what function to use, and what base point to use, or what point of tangency to use. Everything else would be up to you. And the way I encourage people to remember this is say, find the tangent line, solve it for y, that is L of x. Then you just plug into this, whatever it is you're trying to approximate, right? So I'm trying to approximate f of 2. So I would plug 2 into this. Now there is another way to say this. Some people do like to memorize formulas. I'm not like that myself, but if you prefer to think in terms of formulas, here's the theorem. This says if f is differentiable at x equals a, then for any x close to a, L of x will be approximately equal to f of x, where L of x is the linearization of f at a defined by the formula L of x is equal to f primed of a times x minus a plus f of a. Some people do memorize this formula, but it's not anything new. It's just the tangent line solved for y. So that's how I encourage you to think of it. But if you prefer to think this way, that works. And this formula will not be given on the test. So if you, however you want to think about it, tangent line, solve for y, then plug in, or you want to think of it as coming from this formula, if you're going to do the latter, then you need to remember this. But again, I think once you understand where it's coming from, once you get that, oh, the tangent line like stays close to the curve nearby, it's so much more intuitive to just think of it like, I'm going to plug into the tangent line instead of plugging into the function. But either one is correct. They are equivalent. bounds on the error can be computed when you come see me in Calc 2. So it turns out this is what's called the first order Taylor approximation to the function f. You can construct second, third, fourth, nth order Taylor approximations. And each one of those has a known error bound, which you'll be learning about in chapter 11 of Calc 2. But that's really the whole story behind linearization. There's not too much more to it. The other thing we need to talk about in this section is differentials. I kind of hate that your book does this here, because what they do is they think of differentials as somehow being related to this linear approximation thing, and they are not. They're very different. But I do want you to learn the notation. So just definition. If y is equal to f of x, then the differential of y is dy equals f primed of x times dx. And this is maybe the other formula for today that you want to commit to memory. We normally think of dy over dx as f primed, right? This is kind of like just multiplying both sides by dx. I know it might sound silly, but remember dy and dx, they're not numbers, right? They're like infinitesimally small changes in y divided by infinitesimally small changes in x. When you divide those two very small things, you get a normal sized thing. The specific language being used here, where I just talk about dy being f prime of x times dx, is going to be important when we talk about substitution in definite integrals, like changing variables in problems where you're trying to find areas under curves. Turns out this is really important there. The reason your textbook introduces these in this section is because they think of this guy as being like y minus f of a, and they think of this guy as being like x minus a. So if you're really sloppy about it, you can kind of rephrase this thing in this way. But you shouldn't. You absolutely shouldn't. And I'm not going to. And I'm not going to make you do that. And I'm not going to give you homework problems that do that because it's shitty. So don't worry about that. However, you do need to be comfortable computing differentials. So just one or two little examples. We'll come back to this again later. Maybe that's enough. Okay. So if y is equal to x squared, I meant to do like A, B, C's, and D's. Yeah, all right. If y is equal to x squared, then dy would be the derivative of this times dx. So here f of x is x squared, so f prime would be 2x. So I would say dy is 2x dx. If y is e to the 2x, same sort of thing, dy would be e to the 2x, I'll write it as the prime notation, times dx, because maybe here we need to think about the derivative for a second. What is the derivative of e to the 2x?
E to the 2x multiple 2.
Very good, right? It's a chain rule thing. So here dy would be e to the 2x times 2 dx. If y is 1 over x, then dy would be the derivative of 1 over x times dx. The derivative of 1 over x is what?
minus x square minus 1 over x square.
Very good. -1 over x squared dx. Right? So 1 over x is x to the -1. His derivative would be -1 times x to the -2, which is -1 over x squared. And then finally, this guy, we can tie back in with our logarithmic differentiation stuff from last time. dy would be the derivative of ln 1 minus x times dx. How do I differentiate the natural log of 1 minus x?
Chain rule?
Yeah, it's a chain rule thing, right? So this would be 1 over 1 minus x times the derivative of 1 minus x dx. Right, 1 over the inside times the derivative of the inside. That's how you differentiate a log, a natural log. In other words, here, dy would be the derivative of 1 minus x is -1. So this is -1 over 1 minus x dx. These are called differentials. Again, in a slightly more grown-up setting, if we're working from the perspective of differential geometry, these objects are the things that we integrate. And I guess we don't know what integration is. There's only so much I can say about differential forms. To learn more about these, I'll say it like this. About what these mean and why they're special compared to regular derivatives. Google the term differential form. The deeper truth here is that there is actually a connection to the linear approximation thing. A differential form kind of describes how a function is changing nearby a particular point. And it's mostly useful in the 3, 4, 5-dimensional case. I can show you really quickly. So they've got a special page for one form and differential forms in general. These get a little bit complicated. We will be looking at things like this, and the thing inside there is a differential form. Again, it's a little bit over our head, but basically they tell you kind of how a surface looks near a particular point. Let me see if they have any good pictures here. No. Maybe a good picture for one form. Nah, that's just gonna make it worse. What we got? It's all pretty complicated. Yeah, I'll hold off on this for now. This isn't going to help anything. But basically, if you want to study geometry using calculus, if you want to study higher dimensional geometry using calculus, differential forms are the key. It's the way we formalize calculus on surfaces. So if I want to, right now we're doing calculus where our domains are the real line, right? It's this one-dimensional surface. It's just a line. That's our domain. You can do calculus where your domain is a sphere. You can do calculus where your domain is some ripply sheet. You can do calculus on a donut where your domain is a 3D donut, and you take all of your inputs to be points on that donut. Differential forms are the key to understanding functions whose input is that donut or points on that donut. Because it will tell you how the output function reacts to small perturbations in the input along that surface, which can be very complicated, but is hugely important if you're going to study anything like general relativity. So I'll leave it at that for our discussion of differentials. There's really not much more there. Goodness, that's really it for today. I hate to waste class time. Let me see if I'm forgetting any important examples. I don't believe we are. It's just a short section. Linear approximation differentials. I guess we can talk about hyperbolic functions. Let's do that. Let's do that. So here, I'll take a quick look. Yep. All the same shit. And then their treatment of differentials is awful. We're not touching that. Okay, so you see, use linear approximation or differentials to estimate these numbers, right? And these are all things that would be very hard to evaluate by hand, but we can do quite easily, right? I don't know the square root of 100.5, but I know the square root of 100. So you construct the linear approximation, the linearization at 100 for the square root function, then plug in. Same thing for all of these, nothing special. The last bit here, introduce and talk about hyperbolic functions. So this is 3.10, is it? 3.11. The regular trig functions are defined using the unit circle. All right, so we say if you rotate up some angle theta, then this point on the unit circle is cos theta, comma, sine theta, right? And it's the unit circle of 1, 0 here, 0, 1 here. Hyperbolic trig functions are defined using the unit hyperbola. Now, what is a hyperbola? Well, it's a conic section. Like a circle is something you can get by slicing a cone. The unit hyperbola has a vertex here at 1, 0, and then kind of looks like a parabola, except parabolas, don't have any asymptotes. These do have asymptotes. Hyperbolas, they don't just grow out and out and out forever. They kind of asymptotically approach these lines. The equation of the unit hyperbola is x squared minus y squared equals 1 instead of x squared plus y squared equals 1. There's another branch over here. But basically, any point here, if we rotate up some angle theta, will be of the form, we call it cosh theta and sinh theta. The H at the end stands for hyperbolic. Now, you wouldn't want to use this definition to work directly with the functions because it's a rough definition. So better, and surprisingly, cosh theta turns out to be 1/2 e to the theta plus e to the negative theta. And sinh theta is 1/2 e to the theta minus e to the negative theta. And these are what people usually take as the definitions. The hyperbolic tangent is hyperbolic sine over hyperbolic cosine, sinh over cosh. So usually these are what we take to be the definitions because they're much easier to work with. And I think that might require fudging in a factor of 2 to the angles in the original geometric definition. But just take the blue box here to be the definition. I think this angle would actually be theta over 2. But don't panic about that. The geometric definition here, we're not going to work with. This we will work with. So I'll hold here for a second. You can write this down. I'm going to show you the derivatives of the hyperbolic trig functions and a neat connection to complex numbers. For this reason, by the way, some people call the original trig functions the circular functions, right? We call these the hyperbolic functions because they come from a hyperbola. We call the regular ones the circular functions because they come from a circle. All right. Pictures. And there's the graphs. We'll look at that in a minute. But yeah, here you go. So if you rotate, yeah, it is. It's theta over 2. Then that height will be the hyperbolic sine of theta, and that x value will be the hyperbolic cosine of theta. It's cool stuff. Now, why do we care about this? Well, you know, the derivatives of the regular trig functions are very nice. The derivatives of the hyperbolic trig functions are even nicer. So kind of when you look at the differential properties of sine and cosine, the derivative of sine is cosine, the derivative of cosine is negative sine. That's appealing. But wouldn't it be nice oh, hang on. So wait, the first dot on the hyperbolic function graph, not the sine, 0, 1. Yeah, the vertex right here is the point 1, 0. And then if you rotate up by an angle of theta, then you get the point, or theta over 2, you get cos theta, sinh theta. Okay, cool. So again, kind of studying the regular trig functions, the derivative of sine is cosine, the derivative of cosine is negative sine. We get a minus there, and we ask, well, what would we have to change to not get that minus? It turns out this is what you would have to change. So let's look at, I'm going to write these with x's instead, d dx cos x. Turns out, well, not turns out, right? Just using the definition over here, this is d dx of 1/2 e to the x plus e to the negative x. The 1/2 can pop out. It's your constant multiple rule. And then you'd have d dx of e to the x plus e to the negative x, which is 1/2. The derivative of e to the x is e to the x, plus the derivative of e to the negative x is e to the negative x times -1. And now e to the x times -1 is the same as negative e to the x. So this is 1/2 e to the x minus e to the negative x. So the derivative of the hyperbolic cosine is not negative hyperbolic sine, it's just straight up hyperbolic sine, which is good news. It's also true that the derivative of hyperbolic sine is hyperbolic cosine. And there are hyperbolic secants and hyperbolic tangents the same way that you have for the other guys. I'm not going to beat those into you, but d dx of the sinh function, hyperbolic sine, would be d dx of 1/2 e to the x minus e to the negative x, and you can probably see it right away. This is 1/2 e to the x minus e to the negative x times -1, and minus e to the negative x times -1 is plus e to the negative x.
Excuse me, which chapter this one in the book? I didn't see this one.
It's section 3.11. 3.11. And so what did we say? Oh yeah, so this guy is the hyperbolic cosine, cosh x. So we're not going to spend a lot of time here. There isn't a whole lot of stuff for us to do here. It's just introducing some new functions. So the nice thing about these is that the derivative of cosh is sinh, the derivative of sinh is cosh, right? There's no negatives that show up. In other words, these solve differential equations that are nicer than the differential equations solved by sine and cosine. So cosh x primed is sinh x, and sinh x primed is cosh x. Similar, but nicer than the regular trig functions.
Forgive me if I'm wrong, but I thought the sine of x.
Say that one more time.
Oh wait, never mind, never mind.
Oh, sorry. So these are nice, right? This has appeal, no doubt. There's one other thing that makes these really beautiful, and that's how they interact with complex numbers. And again, this isn't some, I will use sinh and cosh as example functions moving forwards, and we will solve problems with them. But in my opinion, the coolest thing about the hyperbolic trig functions is what happens when you plug in ix. Sinh of ix would be 1/2 e to the ix minus e to the negative ix. And cosh of ix would be 1/2 e to the ix plus e to the negative ix. Now, what follows is something that I won't be able to prove for you in this class, but I will be able to prove it for you in Calc 2. And again, it uses power series. Cosh of ix, this expression right here, is good old-fashioned cosine. And sinh of ix is I times the sine of x. So you can kind of go back and forth from hyperbolic geometry to regular geometry by swapping in a complex version or an imaginary version of your variable. This is a consequence from a famous formula that, again, we have to wait until we have power series to prove, which means Calc 2, from the famous Euler identity. E to the ix is cos x plus I times the sine of x. This identity, again, hard to prove, very complicated, not at all obvious. What would it even mean to raise e to the I times x? Like if you plug in pi here, what does it mean to take e and raise it to the power of I times pi? if you plug it in over here, it makes sense because pi, you just get cosine of pi and sine of pi, which are -1 and 0 respectively. But what it means to raise the number e to a complex number power has nothing to do with repeated multiplication in the same way we normally think of powers. It has to be thought of as coming from this power series. And that is beyond us. But these are the nice facts. And these are some nice geometry facts that you may find useful as you move way on in your studies. For us right now, the hyperbolic functions just give us more examples to look at. The graphs, we can take a quick look at. Figure all this out. Does this thing know? It does. All right. Their graphs are very different from the regular trig functions. The regular trig functions are bounded and periodic. These are neither. These are neither of those things. But they do work. You can still get some stuff out of them. I'm not going to expect you to work with these graphs very much, but I do expect you to know the definition of cosh and sinh. I do expect you to know their derivatives, and that'll be about it. That'll be about it for us. I just want to introduce the concept of these things to you because later in differential equations in particular, they will play an important role. All right, I think this is a pretty good place to stop for today. So William, I'll see you towards the end of the office hour. I understand you're busy until the end of the office hour. Just come by whenever you can. We'll talk for a little bit and make sure everything is as good as it can be and ready to go. Next time.
And then I'll be presenting on Wednesday.
Yes, sir. So next time, Wednesday, William will teach us section 4.1 on mins, maxes, inflection points. Lots of graphing. So what we'll be doing is using the derivative to help us answer cool questions about graphs. It's not an overwhelmingly difficult section, but you do want to be comfortable with graphs for it. So if you haven't, take a look at that library of parent functions that I have in our modules. Take a peek over your basic trig functions and stuff. Make sure you're comfortable with those kind of fundamental graphs. And please show up on time, be respectful, because this student teaching stuff is always stressful and scary. So we want to make sure that we show each other all the respect we deserve. That's it from me for today, guys. Please do review your exams if you have not yet. Take a look at anything in there that you want to ask about. The right place for that is office hours. So if you want to talk about, this problem or that problem, bring it by office hours. I'd be happy to look at those with you. And then I'll see you on Wednesday. All right.
I have questions. Did you put extra credit in this exam, the score?
No, there is no extra credit on the test, no.
Okay, thanks.
Will there ever be a chance for extra credit?
No, not as a general rule, no. Alrighty, gang. Take care. If you do want to talk about any grade stuff, that's also good candidates for office hours things. You can email about it too. But whatever you'd like to do. If you're concerned about grades, you want to talk about grades, anything like that, just come see me. I'd be happy to do that with y'all.
Will you have the office hour today?
Yep. Yeah, normal office hour today from 1 to 2.
Okay.
Alrighty, guys. Take care.